Okay, we should start. So what we're gonna do today is first, as usual, if you have questions, they're very welcome. Then we will sort of do a brief recap of how we built the R models of the Bayesian models. We will then build the stand version, do model quality check, run the model comparison, and do the multi-level version. The point of this, I'm actually just going to turn off the light there, is that, yes, we are looking at how we start from a cognitive principle and we implement cognitive models of specific tasks that embody that principle, but also it's an overall recap of the full workflow. So, are there questions on what we did last time? Okay, so if you remember, this is the setup. We have an urn with two different kinds of marbles. Here they're red and green. In the course notes, they're blue and red. I'll make it sure to change that at a later point. And we want to, these urns might have a different proportion of red and green marbles. And at each trial, the urn changes, so we cannot learn, but we'll see if we have time at the end of today how we would implement a learning model. At each trial, you sample n marbles, say 8, that's the first source of information. At each trial, another participant samples in a way that you cannot see, again, 8 marbles, and communicates their guess as to the next marble. Will the next marble be more likely to be red or green? How confident I am on that. Right? And that's the second source. We discussed that in order to model this setting, we can choose at least 2 different ways of doing that. We've actually seen a few more, but here just 2 main ones. One, we could work on the logout space and turn 0 red marbles into 0.1 on this logit scale, so pointing towards green, and 8 red marbles to 0.9. That's the highest possible evidence for red without going all the way to 1, because in logout space, 0 and 1s are infinite and therefore tricky to treat. The same for the other. We can simply rescale confident green as 0.1, confident red as 0.9. Or we can actually do a much more fully Bayesian approach and say, well, we should really model the sampling of 8 marbles as a sampling of 8 marbles, right? Saying that we have a binomial in which we're sampling 8 times, and the number of red marbles that we get is the number of ones in that binomial. And we can do the same for the other, sort of trying to reconceptualize in which kind of space we're moving. So there's 4 possible values. So the obvious choice would be to reconceptualize as 0 to 3 red marbles. And that reflects the fact that in the self, we have direct perceptual access to these 8 marbles. When we look at the other person, we're not seeing these 8 marbles, but we're actually seeing only an indirect index of that. And therefore, only going from 0 to 3 decreases the confidence in the evidence that we get from that person, right? There's nothing stopping you from putting 0 to 8, right? And rescaling it accordingly. This is just one of the possible choices that we make that we need to be able to motivate, and that to a certain extent will become slightly less influential once we introduce weights. Because if we put a very unweighted or a very unconfident evidence source, right, and the participants are treating it as equally strong as the direct perception, we'll see that as a higher weight, right? And then we can discuss. If we put it from 0 to 8 or 0 to 7, whatever it is, then what we see is that this is already modeled as extremely confident, equally as the direct perception. But if participants are downweighting that source of evidence, we'll see a lower weight, right? So the model will find a way to compensate for the exact scale, but we need to make a choice and we need to be able to motivate it. The experiment is built so that you get all combinations of source 1 and all combination of source 2, right? And as I said, all these constraints are annoying and overly controlling. This paradigm was designed to put people in the scanner. You went through cognitive neuroscience, most of you. You know how annoying designing experiments for fMRI is, and therefore the same constraints apply to this experiment, but I have a few slides and a full part of the course notes where we say, well, actually, let's loosen these constraints and make more free paradigms. And then how do we adjust the model for that? Good. We set up the experiment. This is simply just creating the full grid of all possible combinations. We've seen that last time. Then we set up the agents. And we have 4 agents that we're setting up. A beta, which we will develop into a beta binomial this time, has a simple Bayesian agent that takes the evidence at face value and a weighted Bayesian agent that can adjust the weight of the different sources. We also have the log odds, where, again, we have a simple Bayesian agent that simply sums up the 2 evidence sources in log odd space. And we have a weighted Bayesian agents that, again, balances the weights in the log odd space. We simulate the simple beta, right? How do we do it? Well, we have a function, as usual, that has a beta prior and an alpha prior, so the beliefs before seeing the data. It has a blue one, which here it should be red, right? But how many blue marbles out of the 8? We have a total. How many marbles there are in the hand when you sample? We have the blue 2 and the total 2, which are the same for the other, right? If the other is saying I'm actually not that confident, but I bet on red, right? That would be a 2 blue, sorry for the confusion, and 3 total, right? We calculate how many of the non-blue marbles there are. And then what we have is that the posterior for the alpha parameter is equal to the alpha prior, so the previous belief, plus the number of blue marbles in our own sample, plus the number of blue marbles according to how we coded the other input, right? That's really the beauty of the beta model, that we just sum up the evidence. The beta posterior, which is the number of zeros or the numbers of non-blue marbles, this example, is beta prior plus red 1 plus red 2. Yes.
Before even seeing the marbles, how many do I expect them to be?
Yes.
The alpha prior would be like either 1 or 2.
Exactly, yes. And then what we can do is what I did in the simulation and in the course notes, I simply set it at 1, right? 1 and 1. So it's the flattest beta prior you could imagine, right? It's a uniform distribution. We don't really know anything. But for instance, you could have a stand model using those as parameters and trying to infer the priors of the different agents, right, as they play the game. It corresponds to what we would call a bias, right? We've done that in previous models. If there is a certain propensity to pick a blue marble, that even, no matter what the others and my direct experience of the word say, then I could have a higher alpha prior than beta prior, right? So it corresponds to a bias in the direction of things. Then we can calculate the posterior statistics in a slightly dissatisfying way, but it's very simple, very computationally light, and we'll see a better method later. But it's really saying, well, the number of blues according to my posterior divided the total number of samples according to my posterior. So the total number of non-blues plus the total number of blues. What's the proportion of blue that I expect in the next round? Here we can see, I can't remember who went through this slide, but basically we can see in red the social evidence, in blue the dark evidence, and we can see how they combine, right? You can see on the top left, we have that the dark evidence says 1 blue marbles compared to 8, and the social evidence says 0 blues, right? And you can see that the red is really peaked at 0, and the blue is slightly moved to the right. And then we see that the posterior sort of hones in the middle ground and gets more confident because those two evidences are really pushing both towards non-blue. Right? It's perfectly symmetric on the bottom right, right? And you see all the intermediate case in the middle. Does it make sense? You can also see that the red lines, let's say here, right? Second from top and second from left, right? We see that the red data, the red evidence, the red source of underlying rate for the social evidence is more confused, is less confident than the blue one, right? And that follows from the way that we coded the data, right? We said that the social evidence comes from sampling 3 marbles, right? You have a question?
I think it is
Yep.
weight in one,
Yes.
but with weight, depending on how many cups, right? So if seven,
Yep.
is
Yes. So the question for the people on Zoom is it a problem that we have made a choice where social evidence is coded on 0 to 3, where we could have made other choices, and that has an impact on the exact value that will get estimated for the weight, right? And the answer is it's only a problem if we go blind into the night, right? So if we don't take that into account. Once we have empirical data where we don't really know how many of these marbles that we should conceptualize the other persons as, the weight might become, let's say, double as high as for the dark evidence. And we should be very careful in saying, but we know that the scales are not the same. Therefore, we should rebalance it that way. Or we could make the choice you're making, right? That's saying, well, actually, maybe we should conceptualize them on the same scale so the coefficients are more directly comparable. And that's more elegant. What's less elegant is that you are sort of parsing a space in equal fashion, right? So you're saying, oh, it can be 0, it can be 2, it can be 4, it can be 6, and you're leaving those gaps in, right? But we can live with that, right? The important thing is that we always keep in mind how we're conceptualizing the different scales. Good. Here is the same data, just summed up. That is the propensity of the agent to pick blue as the next plausible marble as a function on the x-axis of the number of blue marbles in the dark sample, and in colors as an impact of what the other is saying. Clear red, maybe blue, clear blue. Right? And we can see that there is, here on the left side of the panel, according to what the social evidence says, we have a different propensity to pick blue, even if there is no evidence. So that means that the agents, as we have coded them, are clearly influenced in a linear way by the social evidence, which makes sense because that's how we program them. And they grow in their propensity to pick blue, again, in a linear fashion. There is a slight nonlinearity that you can see in the confidence, because what happens is that if the two sources are going in the same direction, the posterior becomes more confident, right? So the confidence becomes bigger, the variance shrinks. As we move into the weighted beta, we again make a function which has exactly the same parameter, but it also has a weight for direct evidence and a weight for social evidence, which gets directly multiplied to both the evidence for blue and the evidence for non-blue. The same weight, the weight of direct gets multiplied both by blue 1 and by red 1. The weight for social gets multiplied for both the zeros and the ones in the other. Right? It weights them both. It's the same. We then calculate the posterior exactly like before, except that instead of adding the darkly counted blue, we add the weighted blues. For the beta, we add the weighted non-blues. Right? Now, somebody could say, wait a second, right? Let's say that the weight is 0.9, right? We see 3 blue marbles. We multiply it by 0.9. Now we get a 2.7 marbles. Does it make sense? Anybody has an intuition? Yes? Mm-hmm. Yep. Yes, exactly. So repeating it for the zoom and rephrasing it slightly. So while the beta has an obvious intuitive interpretation in terms of numbers of blues and red marbles, it's not bound by integer numbers, right? It simply says, well, slightly more evidence on the left, slightly more evidence on the right, and then I should have actually made a plot, but then we simply have that these distributions move a bit, right? The fact that it's an integer number is not a boundary of the beta distribution. Good. Then we calculate the expected rate exactly in the same way. Alpha posterior divided alpha posterior plus beta posterior. And just because I want to make a plot after, then I also calculate the variance according to the formula of the binomial. So what we see here is the behavior in two different scenarios. In the first scenario, we have strong direct evidence for blue, 7 out of 8, and strong social evidence for red, 0 blues out of 3. On the x-axis, we have the possible weights for direct evidence. On the y-axis, we have the possible weights for social evidence. And here I bound them between 0 and 2, though there are no natural boundaries. 0 means that that source of evidence is not given any role at all in the decision. 1 means that that source of evidence is taken at face value, just like in the simple agent. 2 means that that source of evidence is considered as twice as important, as if we had sampled twice as many marbles and gotten the same proportion, right? So we get more confident. And what we can see is that the decision is skewed, right? So that most of the decisions are for blue and fewer are for red, but there is a decision boundary that sort of mediates between the two. A few more words on that in a second. Below here, we have weak evidence for blue in the direct perception and strong social evidence for red, right? And what we see is that, again, we have a trade-off between picking blue and red, which is not symmetric, right? And there's more red than blue, but not as much as before. Why am I spending words on this? Because these should give us another representation of the fact that the two sources of evidence count for different weights, or not for different weights, but they bring different strength of evidence. So that if we have 7 out of 8, it will count for more than almost even 0 out of 3 for the social evidence. Right? Also, I'm showing you these plots because it's very important when you build your models to figure out ways of representing the way that they work. As we get to more and more complex models, there are no standard ways of doing that. And so I'm just regurgitating different plots of how to represent these models. We then do the full set of scenarios here. So we're seeing in the x-axis the dark evidence, 0 to 8. On the y-axis, the belief in the next peak being a blue marble. On the now I cannot see it very well, neither can you, but it's better in the course notes. But we can see that we vary the weight for social evidence on the columns and of direct evidence on the rows. So we can see all the first column, basically there is no impact of social evidence, right? Because the weight is 0. And on the top row, we see no impact of direct evidence because the weight for it is 0. And then we see that as we increase the social evidence, there is a bigger and bigger spread between the 4 lines. As we increase the direct weight for direct evidence, we get a steeper and steeper slope, right? All of these is still very linear, right? We can also simulate the log odds. And there suddenly we start seeing very different behaviors. Right? So here we have that on the x-axis, there is the log odds for evidence for blue in source one. On the y-axis, again, the belief that the next marble is going to be blue. And in different shades of blue, we have the evidence in the other decision. The formula there, the function there, it tells us that what we're doing is we have an inverse logit scale of bias plus logit of source one plus logit of source two. Right? And bias is put there, so it's equivalent to the prior in the other model. And if you look at the plot, right, we're seeing something that follows the same general pattern, but it also has some important distinctions. What's happening there? Yes? Yes? Mm-hmm. Yeah. So instead of adding up in a linear way, the evidence for the two sources adds up to the maximum spread in the middle. And as you get closer to extreme evidence, it gets non-linearly added in an asymptotic way. Right? This is, a consequence of plotting things, or not plotting, but conceptualizing things in the logout space, where 3 plus 3 is not very different from 3, right? While 1 plus 1 is actually quite different from 1, but is also a conceptual consequence of these model conflating two different aspects of the information. One is the evidence in favor of blue or red, and the other is the confidence in that evidence. We've seen before that the nonlinearity was in the confidence, right? While the expectation was linear. But here we don't allow those two parameters to be separated from each other. And therefore we get these nonlinear effects. We can also do, I'm going to skip that part. We can also do the weighted Bayes in log odds. And I'm not going to go too much through the details of that. But yeah. But once we visualize it, just like before, again, we get the same nonlinear effects, right? We can see that the information is compressed at the end. When both sources are in agreement, they tend not to add too much to each other. And again, right, if you are in doubt, right, which one of these is the best way of conceptualizing our data, a first step is to go and look at the empirical data and see which, like the nonlinearity effects are quite clear. And we can do model comparison. Good. Now we are gonna run the stand stuff, but I'm actually gonna focus on the beta model because otherwise we'll never running done today. So we're gonna make 3 scenarios with three different agents that are simulated. We're gonna take basically the simple beta agent, has a weight of direct of 1, a weight of social of 1, and we see exactly the kind of patterns that we've seen before. We then have, I gave it a name. Now I have to remember what it was. Oh, the self-focused agent that is really giving 1.5 weight to their own experience and 0.5 weight to the other experience. Right? And what we see is that the same pattern as in the previous plot, but everything is squeezed. The social information is not really differentiating that much. Right? We then want to have the socially conform or socially influenced, where we give a weight for direct perception of 0.7 and a weight for social information of 2. Right? And we're simulating 3 scenarios because then what we want to do in the next step is we want to build STAN models that are fitted to these data. And we want to see which of these model is preferred by the model comparison and the model quality checks. And if we have a balanced agent, that will correspond to the simple agent. If we have unbalanced agents, we should expect the weighted base to be a better model. But we are sort of messing up with the different weights so we can see whether, for instance, our choice of scale impacts our ability to reconstruct the model. Also, 3 is rhetorically effective. Good. We also look at the confidence, right, which I had calculated before, and we can see that the confidence raises at the extremes, right, when the 2 sources of evidence converge. Our models is more confident in their final expected rate. We can see that it drops in the middle. And also in the extremes, we can see that if so we can see in the purple is clear blue, so it's in contrast with the direct evidence, that's for the red. So the confidence is at its relative lowest, and then it goes to its relative highest when it agrees with the other source. It's perfectly symmetric in its weird fashion. When we look at the self-focused person, again, it's just more shrunk because the other is not affecting their confidence as much. When we look at the socially influenced, we get a much bigger spread because the higher number of samples in the direct evidence sort of slightly compensate for the lower weight in direct, and the high weight in social is sort of emphasizing the information in the other. So when they diverge, they really diverge. Good. So finally, we get to STAN. And here is a simple agent for the beta distribution. In the data, what we do is we give it how many trials there are. We give it an N. We give it how many blues there are in the direct evidence. Blue 1, it's an integer. Its lower value is 0. And it's part of an array because that happens as many times as the trials. We give it the array of total, how many times, how many marbles are sampled, which again, we could have put it as an integer, but that gives us more flexibility because we can change that, right? We could make a simulation where sometimes you fish 5, sometimes you sample 7, right? And then we do the same for blue 2 and total 2. And finally, we have as the second piece of data choice, what the model is actually choosing. Integer array, the lower is 0, the upper is 1. We then have the model, right? Each observation is a separate decision. So for simplicity now, I'm just making it a loop. So it loops through each decision one at a time. As before, we calculate alpha posterior, which is a real number and not an integer. Here I hard-coded, I should have made it a parameter, the alpha prior plus blue 1 at the place I plus blue 2 at the place I. the beta post is a real number, and it's the beta prior plus total 1 at the place 1 minus blue 1 at the place 1, so the number of known blues, plus total 2 at place I minus blue 2 at the place I, so the non-blues at social evidence. We then put the real expected probability, which we calculate exactly like before, and then we say that the choice at time I is given by a Bernoulli distribution with an expected probability. Does that make sense? Right. I'm not going to go through the generated quantities because you should, at this point, jump on the chair and say, you sucker, right? You keep ranting about full Bayesian uncertainty. We do Bayes because we can do all these things. And then we feed the Bernoulli a pointwise value, right? As I said, right, this is very convenient. The expected probability can be calculated as a one value, which is very easy to deal with, as the number of blues divided the total number of marbles at play. But these also sort of forgets that if the total number of marbles at play is 100 or 10, the confidence in the expected rate should be very different. Does that make sense? So here I'm introducing formally the beta binomial. The beta binomial is a distribution which has an outcome that's binary, like binomial, but instead of having a rate as its parameters, it has the alpha and the beta from the beta distribution. So we can see here that everything in the data and in the model is exactly the same, except for the last part where we calculate the expected rate and we put it in the binomial choice. Here we say that the target is plus equal a beta binomial log probability mass function, where the choice at time I is given by, well, we're only dealing with one trial because it's still a binomial. And then we have an alpha posterior and a beta posterior. In this way, instead of us doing the trick of calculating the expected rate, the model puts in the full distribution of the underlying rate. Does that make sense? Does that make sense? Yes. So before we said, right, we're using the beta trick where we have an alpha and a beta, which define a distribution of the underlying rate, right? 0 and 1. So the beta is this, and it's generated starting from the two parameters, alpha and beta. And then for simplicity, since the alpha is the n of ones and beta is the n of zeros, we can say, well, the average expected rate is simply alpha divided alpha plus beta. That is the number of ones divided the number of ones plus the numbers of zeros, meaning the total number of marbles that we sampled, right? The proportion of blues is given by the number of blues divided blues plus reds. And the problem with that is that basically we are taking one number to describe an underlying distribution, which forgets that the underlying distribution might be very confident or it might be very broad, very unconfident. It was very convenient, but we can actually feed to the model the full underlying distribution. And we could go through a model that says something like target plus equal. We have beta LPDF, and then we have the rate over alpha and beta. Right? That would give us a distribution, and then we could say that the target for the Bernoulli, which is a binomial with an n of 1, Bernoulli LPMF is choice given rate. Right? So we would infer the full underlying distribution of rate in the beta, and then we would feed that rate to the Bernoulli. Since this is a problem that we're not the problem, it's a conceptualization that we're not the first ones to deal with, there is a distribution that actually does this in one step, does these two steps in one. And that's called the beta binomial. Beta binomial LPMF, where the choice is given by trials because it's a binomial. They didn't do the beta Bernoulli, alpha, comma, beta. Right. Which means that we're not just taking the average of the underlying mean and throwing the rest away. We are actually feeding the full rate distribution to the model. Comments? Yes. That's a good question. In all of my simulations, I haven't, because in a sense, the model, our our agents might be very confident, discard all the information, right? It makes things much simpler. It's more when we do an inference from existing data that we want to actually give uncertainty the right weight, right? But we could make agents that work according to the beta binomial. That wouldn't be a problem at all. It's more, it has to make a decision at some point anyway, and part of that information will be lost anyway. But given that as inferential agents here, we want not to be overconfident in our inference, then it's actually more important at this stage to add that part. But also it's pedagogical build-up, right? Yeah. There's also the generated quantities where, again, whenever we generate the posterior predictive choice and the log likelihood, we change the Bernoulli we're using before with the beta binomial. But Stan is nice because it doesn't have everything implemented, but when it implements a function, it implements all the versions. So the LPMF and the random number generator, for instance. Good. So the beta binomial is exactly a distribution that takes alpha and beta, infers the underlying rate distributions, and uses that to generate a binomial outcome. We then want to have the weighted agent using the beta binomial distribution. The data is exactly the same. The parameters are now weight direct and weight social. And that reminds me of something that I might not have emphasized. Where are the parameters here? In the simple agent. Yes? Yes. Yes. Yeah. So does it make sense to make a Bayesian model without parameters? Yes.
Basically, this could also be written without the stack rule. Like, I think it may be wrong, but you're only thinking
Yes.
that you're going to provide like
Mm-hmm.
on theory.
Yeah. Yeah.
Because we already know what the distribution looks like. Yeah.
Yes. Okay. So the point is, in this case, we have a model that's not probabilistic. It's deterministic, right? It's not inferring anything from the data. Oh, yes. But it's making prediction, and their fit to the data can actually be evaluated. So we can build it in R, but for having all the same workflow as the other models, we can build it in Stan and then fit it. And it will tell us how well that model without parameters will fit the data. And it will, of course, complain when it does the Hamiltonian Monte Carlo because it doesn't have anything. It's moving in a zero-dimensional space. And using models without parameters is actually kind of the holy grail of modelers, because we all know that as soon as we add parameters, right, we can make almost anything fit to everything, right? So there is a whole line of researchers who really works hard to eliminate parameters as much as possible. But in the weighted Bayes, we actually have the weight for direct, the weight for social. We have a prior for the weight for direct and the weight of for social. Here I put them as normally distributed with the mean at 1. So they're giving equal weight to both of them, taking them at face value, and a standard deviation of 0.3. Why? Because it goes roughly from from 0.1 to 1.9, and that seemed like a reasonable region of thing. As usual, we do model quality checks, and we figure out whether that's a good idea. Then for each observation, we calculated the weighted blue, the weighted red for the direct perception, the weighted blue and the weighted red for the social perception. Then we calculate the beta parameters by summing things up. And then we use the beta binomial, right? So the only difference from the previous model is that now we have the two parameters, we put priors on them, and we multiply the evidence for each source with the weight for that source. Have just one last point before I let you go for a break. Is this all good? Does this model make sense to you? You suckers. No, sorry. Yes, it seems to go all good, but as always, when we do cognitive modeling, we will meet some challenges and we'll have to do something with the model. But for now, let's take a 10 minutes break.
Yeah, I think it's well,
I'll be fine. That's optional.
like this.
The point is that you get to show up whatever you mentioned or something. Paying for nothing that if they are paying for it, nothing they are signing.
They have to update. It's really to be
Okay, we should restart. So what we have now is we have data that we simulated from the R models. One that should fit best the simple Bayes, and two that should fit best the weighted Bayes. And we have two different scenarios with uneven weights that we expect the weighted model to nicely reconstruct in terms of which of the sources of evidence is more weighted. So we go and fit the models. We run the first model, and what we get is something that's slightly different from what we've got before. So we get that the model is running, it's compiling, it's running, it finishes in 100 milliseconds. And then we have a wording that says 2 out of 2 chains have an NaN EBFMI, meaning that the 2 chains, so we're trying to evaluate whether they're exploring the posterior space in an equally spaced and distributed way. And instead of having a measure of how well they're exploring the posterior space, they're just an array of NaNs, not a number. Why is this? Well, there's no Hamiltonian here. There were no parameters. So in this case, we shouldn't worry. Is this useless? Well, we discussed it already, so I can skip that. Then we can run the weighted model. We get no warnings. We look at the hairy caterpillars. Can you see anything problematic here? I know they're small and they're far away, but there's nothing particularly worrisome. Then we check the prior predictive checks. And then we see that according to the priors, before we see anything, the expectations are 50% blue, 50% red. And I removed the broad confidence intervals because otherwise it would cover everything, right? The model expects everything. And when we look at the simple balance, simple focus, and simple social influence, again, we get the same expectations because before looking at the data, we know nothing. We can look at the posterior predictive checks, and we can see the posterior predictive checks on top for the simple and on the bottom for the weighted. Before, in the prior predictive checks, they were exactly the same. And so what we can see is that after seeing the data, the simple model still expects that the direct evidence counts in a linear way and that the social evidence sort of nicely detaches the decision boundaries. As we move across the 3 scenarios, the predictions don't change even after we've seen the data. Because there's no parameter to be fitted. There's no way for the model to change their beliefs. When we look at the weighted model, we see that they're slightly less spaced than above here in the balance. They're even less spaced when the model is self-focused. And they're more spaced when the model is socially compliant, which is exactly what we expect. In self-focused, the impact of social evidence is decreased, so it doesn't make as much of a difference. When we look at the socially compliant model, the social evidence is increased, so it's more spaced out. So far, everything looks good, right? No warnings, good trace plots, good prior predictive checks, good posterior predictive checks. Then we look at parameter recovery. And here I skipped a step. I've actually ran a bunch of different weights just to see what happens there. And what we can see is that on the x-axis, there's the true direct weight. On the y-axis, there is the estimated direct weight. And then I added as a color how many times the model is exposed to each combination of the two sources of evidence. So that we can see also in a kind of a power/precision analysis whether if we see issues in the fit of the model, in the ability to reconstruct the true parameter values, if that's something that we can solve just by feeding it more data. I know they're small and far away, but anybody wants to comment on the plots? Just giving somebody else a chance, then I'll, yeah. Yes?
Yeah, continuously overestimates the weight.
Yes? Exactly. Yes, not only that, but also, so most of the values are above the diagonal lines. So it's overestimating the weights, but also it's not really making a difference for higher values, right? It's kind of flat. Yes, Lavitz? Yes.
Yeah. I think a good point that also point out is that it actually estimates the parameters to go above 1.
Yes.
Which is a weight structure might have some interesting implications
Mm-hmm.
with the estimated weights might be able to go into the negatives, which also is
Can they go into the negatives?
it's taking an unweighted total and then it applies the weight to the counter groups and the estimated weight groups. So it makes it so if it's above 1, then you could theoretically see more groups than there are total counts.
I think what we weight is the total minus the blues.
Yeah.
So we first subtract.
Yeah, but I think is that the blues are
Mhm.
by weight.
Yeah.
And let's say the total, all of them are blue. And wouldn't that total amount of blues to be of the total?
No, because the total amount that goes into the beta binomial is alpha post plus beta post.
Okay.
Yeah.
So this
But yes. But you're hinting at something, right? You're saying, oh, wait a second, right? Now we're saying that weights can be above 1, right? And are we sure that if we actually, let's see, so the social is the same, right? But the issue might be that the combination of the two weights might be difficult to identify, right? We discussed it last week, right? We might have, so this model should be able in principle to deal with that, but apparently not. We might have that a weight of 1 direct information and 1 social information will give very similar results to a weight of 2 social information and 2 direct information. Because they are pushing it towards the same mean expected rate. The variance of the expected rate is going to vary. It's going to be different in these 2 scenarios, but the mean is going to be exactly the same. And 3 and 3 is going to be exactly the same, and 4 and 4 is going to be exactly the same, and 20 and 20 is going to be exactly the same. So there might be something there that makes things difficult to estimate for the model, right? And so here, when I so it didn't work, right? I could put in the don't give in, don't give up song.
So what would you do? Right, after you cried a bit and you had your friends pick you up. Yes, Balazs?
Could we somehow like, restrict possible weights or make them relative to each other? Like,
Yes.
if one of them is twice as weighted, then we assume that the other is half as weighted, maybe. Because we need a combination of possible weights.
Yes. So here I'm saying that we could put strong boundaries. For instance, we could say that the weights can only be between 0 and 1. The second is that the second weight is a function of the first weight, and then we can figure out what function is. Was there a point there coming? No. No. Yes. Other? Yep.
I think I would also try to fix one of the weights and to see if fixing one of them actually allow them to be to see when failure moves up. And that's
Yes. This is a really good idea, right? So the idea is we have a model that doesn't do what we want it to do, though it doesn't give us any signal that it's not doing what we want it to do. So one of the things that we can do is we can start simplifying it and see where the issues are emerging. And let's say that indeed you fix one weight and you find that the model can reconstruct the other weight. How would you proceed then?
it could be then either is we might see it was the other way, well, but the
So if you only have one weight, no matter which of the weights to estimate, the model performs.
yeah, then it still performs. There's no bias in the way it covers the other. It's gradually and to become this and this fixed by with fixed fixed okay, small boundaries, but exactly.
Yeah, so I see where you're going. So basically you're saying we can fix one weight, the model is simplified. We simulate data only with that fixed value for that one weight and varying the values of the other weight. The model works fine. We do the same with the other weight. The model does fine. Maybe we should find some compromise between fixed and fully inferred parameter. And the way you're going there, it's very hacky and it's going to take a lot of time and it's going to be hard to justify. So a more general way of doing that would be to do this. Right? Would be to constrain the value of one weight given the value of the other weight. Yes.
So this could be this problem solved of one and two if they are approximately in the same relation between them.
Yes.
Then it actually seems like when it's a 1 and a 1, 10 and 10, it was the steepness point.
Mm-hmm. Yeah.
But then I guess try to simplify it by instead of figuring out two weights, then simplify it to one. That was like the weight relationship.
Yes. So for instance, a first way is simply to say weight direct and 1 minus weight direct. Right? This says that the two weight or 2, right, according to how we bound it. So we say that the total is equal a certain amount. Let's call it big T now. And then we say that T is equal weight 1 plus weight 2 which means that, for instance, weight 2 is equal to t minus weight 1. Right? So what we've done is we say we assume a certain level of total confidence, if you want, a certain level of masked evidence in the model. And then what we do is we say that the model has to apportion, has to divide that amount of evidence between the two weights. Does that make sense? Do you see any drawbacks with this? Yes?
Surely the protection something with this thing regarding the linear or the relation between the two weights. Once it fits it, there is this is if the t isn't restricted between one, if t isn't one, then the x might just be no. My first intuition was to give a parameter that would explain the kind of the relationship between the two weights. But I guess in the weights own distributions, you have to say that weight 2 is like 4.6 times weight 1. So it's implicit.
So the way I'm imagining it is that you have that weight 1 is equal to these, I don't know, weight proportion, and weight 2 is equal 1 minus weight proportion, or is that different?
Yeah. Yeah, I guess that way of writing it makes more sense to me than the total weights. Is it kind of the same?
It's more flexible. Yeah. So if you're getting a bit lost, the basic idea is that if you remember, we have two components of the final rate. One is the mean, right? The expected rate. That mean is purely determined by the relative proportion between the two, right? As we said, if we have weight 1 or weight direct equal 1 and weight social equal 1, we're going to get these expected mean. If instead we have 2, we're going to get exactly the same expected mean. If we get 5 and 5, we're going to get exactly the same mean, right? But what's going to vary is the variance around that expected rate. So what we're trying to find is a way of reformulating the two weights, weight D and weight S, that allows us to calculate both parameters, but constraining the one weight with the other, right? So that they cannot really go all sort of directions. And so that's exactly what we're going to try to do. We're going to have a parameter that tells us how much evidence we want the system to have, how confident our expected rates should be, and a parameter that sort of tells us the ratio between the two weights. And the way that we do that is we have now as parameter the total weight, the total influence of all evidence, and the weight the proportion of weight for direct evidence. Then we have a new chunk, that's the transform parameters, which we've already seen in the multi-level modeling, where we define weight direct as total weight times the proportion for weight direct. And for weight social, the total weight times 1 minus the proportion for weight direct. Then we have two priors. One is for the total weight, and now the total weight is a positive number, right, that can go up to infinity. So I give it a log prior, and then I center it at 2 with a reasonable spread, which in log space is a mean of 0.8 with a standard deviation of 0.4. And for the weight proportion, given that it's a proportion, it goes from 0 to 1, I put a beta prior. And then everything else is exactly the same, right? Because all the work is done up there. When I first started meeting these sort of reparameterization, I had the strong urge to throw this away and say, what the heck? Mathematically, it's exactly equivalent. Right? But we have reformulated the weights in a way in which their parameter estimation is constrained, the one with the other. And I've been asking people, and I've been trying to figure out, what's the general theory of reparameterization. It's not there, right? It's a question of meeting a lot of examples, getting a lot of tools, and trying out things until it works, and then slowly you develop an intuition. I hope there will be work on making it more systematic. But when we then go and look at the trace plots, we get no divergences, no low energy, no low effective samples, no issues with R hat, nice hairy caterpillars. Prior predictive checks are exactly the same. Posterior predictive checks are, like before, actually slightly more clear. We look at the prior versus posterior update checks. In red, we have the priors. In whatever color that is, gray, we get the posterior. And we see here in the scenarios how there seems to be some sort of posteriors following the true value. But now we're very skeptical because we've seen how terrible it was all before. And then what we look at is the parameter recovery for the new parameters. You can see on top the total weight, which is not very good, right? We look at the proportion for the weight and the 1, it looks better. But really, we don't care about these parameters, right? What we care is how well we're trying to recover, we're able to recover weight for direct evidence and weight for social evidence. And this is much better than it was before. Right? It's not perfect, but especially if we zoom in with the 5, we get very good fit. And here I also represented in terms of absolute error in the parameter reconstruction, right? How does the parameter of recovery error changes with increasing number of trials? We can see that there is a clear decrease as we increase the number of trials. On the left panel is in absolute terms, on the right panel is given the average value of that parameter. Good. So what we do is we now run the model comparison, right? We add the LU to those models, and then we look at how the LUs look like. Of course, the LUs are telling us that the model is crap at predicting when it's a simple Bayesian model, because it's not really fitting the data. But all the 100, 180 data points are nicely predicted in the weighted models. Then we look at the model comparison. We see that in terms of the ELPD difference, so LU compare, for the balanced model, the best model is the simple agent. For the self-focused model, the best model is the weighted agent. For the socially influenced data, the best model is the weighted agent. And then we can also do the new weights, look at whether you adding the one to the other helps us making better prediction. For the balance scenario, it says no, just give 100% weight to the simple agent. For the self-focus, it says the simple agent might add a tiny bit, but really 91.5% of the weight should go to the weighted agent. And for the socially influenced, we have 100% for the weighted agent model, which means that not only we can recover the parameters correctly in this little universe where we have only two possible models, we are quite accurately able to reconstruct the model that has generated the data. And then we can look data point by data point, which are the problematic ones. And so in the middle one, we could go and check which are the data points that are generating some local better fit of the simple agent model. But what I want to reach today is actually the multi-level model, because then what we can do is we can look at the model comparison, not as much at the global level, but on a participant by participant level, which is something that's not usually covered in model comparison techniques. So what we're going to do is, I actually changed it. So we're going to have 20 agents that have a population level total that's centered around 2. And the ratio, now I changed it. I can remember, I think it's skewed, but I can't remember how skewed it is. It's in a later slide. Because of course I was running a multi-level agent simulation in which there was a simple agent simulation with then 20 agents that were only varying some small stuff. And then the weighted base in which the agents were again centered around the balance scenario and varying slightly on that. And then the model was having trouble separating them because they were equivalent to the simple agents. So now it's a different ratio. I can't remember. I'll check it. So we run the simulation. We sort of look at the distribution of the weight in the simulated agents. On the x-axis, we look at the weight for direct evidence. You can see it's centered at 1, but it varies from almost 0.8 to 1.2. For social evidence, we get that the average is 0.6, and it varies from 0.7 to 0.4. Right. So the simulation has worked. It creates agents that are not balanced and that vary on these different parameters. Then what we need to do is we need to take the simple model. We need to adjust the data chunk so that it can take matrices instead of arrays. We need to adjust the parameter and the model. So as we will see, I'll do it step by step. So I'll say that the simple agent has a scaling parameter, meaning as a total weight. They cannot change the ratio between the two, but some agents might be more convinced and others less convinced. And then the weighted agent has both the scaling and the weight parameter, both total and weight parameter. We'll then need to add the individual and the population level in the model. We'll need to z-score the individual variability. And we will need to model a correlation between parameters. And then we need to do the same for the generated quantities. Oh, and this is again in the way. Good. So when we look at the parameters for the simple agent that has only the scaling, we can see that there is a real parameter that's called mu scaling, the population mean for the scaling factor. We have the sigma, the standard deviation, the average error that we would get if we try to predict an individual from the population level. And then we have the individual level parameters, which usually we would call the random effects. So a vector of a certain length, as many as the participants or agents, called z-scaling. Then we have the transform parameters. We have that the scaling factor, the individual scaling factor, is given for each of the participants by the population mean plus the individual variation of that participant on a normal distribution scale centered at 0 with a mean of 1, multiplied by the sigma. What is this? This is again what we've seen already. It's the rescaling and normalization of individual variability, because the model tends to sample much better when that parameter, z-scaling, is distributed along a normal distribution with a mean of 0 and the standard deviation of 1. Therefore, we extract the mean, we subtract the mean, and we multiply by the standard deviation. Then we have a model where we put a prior on mu scaling and sigma scaling, where the prior for mu scaling on a log level is a normal with a standard mean of 0 and the standard deviation of 1, which puts its mean at 1, and a very broad standard deviation. The sigma scaling, again, I made it very broad and exponential with a rate of 2. We could plot it, but time is running. Then we put a prior for the standardized random effects. And as we've said, we put these very prior that their center is a normal distribution center at 0 with a standard deviation of 1, which in Stan jargon is called a standard normal distribution. And then what we do is that for each of the observations, we say that the scaling factor is the scaling factor of the agent that corresponds to the line. We calculate the weighted blue and weighted red, because in this case, now we're adding how confident they are. But we don't include any asymmetry between the two weights, in that we use exactly the same scaling factor for all the sources of information. We calculate alpha posterior and beta posterior, and then we have the beta binomial, just like before. When instead we look at the multi-level weighted agent, right, what we have is we have not just the mu scaling, but also the mu weight ratio, which means that we need to have two different standard deviations, the sigma weight ratio and the sigma scaling, and two separate vectors, the standardized weight ratio for that participant, the standardized scaling factor for that participant. Right? We then do the same thing that we've done before in the transform parameters, where we actually transform the weight ratio and the scaling factor so that there is a mean that's external at the population level, an individual variation multiplied by the standard deviation. And also want now to calculate separate weight direct and weight total and weight social, which are not separate parameters. They are fully derived from our formula here. So that we have that weight direct for that participant is given by the scaling factor J times the weight ratio divided 1 plus the weight ratio. And so the total times how much evidence there should be for relative evidence there should be for direct. And then and then it's normalized. And then we have that the weight social, again, is the scaling factor divided by the proportion that they have, the ratio that they have. We have then a model that, again, priors for the mu weight, prior for the scaling, priors for the standard deviations, normal, prior, standard for the individual levels of the parameters. And then we say that for each observation, we first extract the weight direct and the weight social for that person. We calculate the evidence at that observation. We calculate the alpha and beta cost, and then we do the beta binomial. Right. So this is, I'm not going too much in depth in how we've ran the multi-level because we've done it already, but please ask questions if there are issues here. Okay. So then what we want to do, what I want to show you is how we can use model comparison in a slightly more nuanced way. So what we do is we merge the data generated by both models. So now we have 40 participants, and we don't know which one is generated by a simple Bayes and which ones are generated by a weighted Bayes. And then we see how the models behave when we try to fit the multi-level model to all 40 participants. Because in the real world, we won't often know these are part of population A, these are part of population B, right? We might have heterogeneity in the participants, and it's important to be able to see that, right? Therefore, we actually skip at this stage the population parameter recovery, and we just go to individual parameter recovery and model comparison. It also makes no sense to have a population level parameter recovery because we're mixing two different populations. So here is, in red are the agents that were generated using the simple model. In blue are the agents that were generated using the weighted models. And first plot, we see on the x-axis the true scaling factor and how well it's recovered by the simple model. Estimated scaling factor according to the simple model on the y-axis, which is definitely not ideal, right? There is no clear diagonal there. In the second panel, we see the true scaling factor on the x-axis. On the y-axis, the estimated scaling factor according to the weighted model. And again, not very good, right? The model is really being messed up by having a mixture of parameters, of agents. If we look at the weight ratio recovery, how well can the weighted model recover the true weight ratio? So we have that for all the simple agents is 1. And for the weighted agents, it's spread out. And what we can see is that there is kind of a diagonal disposition of the weighted agents, but the estimates also for the weight ratio of the simple agents is completely off. Right? The model is clearly not able to reconstruct the true parameter values for this mix of agents, which makes sense because the model assumes that they were all produced given the same mechanism. I could have hoped that the weighted model could reconstruct that the weight proportion for the simple agents was at that level, but it's clearly not able to do that. So what we do is we do the usual model comparison, right? We add the Lu, we ask for Lu compare, we ask for the model weights, right? And then we plot it. And it's telling us that all in all, the weighted model is much, much better than the simple agent model at describing the whole data set. And if we were analyzing empirical data, we don't know the true underlying values, right? We don't know that there is an underlying mixture. So sure, right? Let's go for the weighted base and let's accept the parameter values that are estimated for the weighted base. But in this scenario where we actually know things, we know that that would be wrong. So this tells us that we should be very careful in going beyond these kind of approaches. So what we can do is we can calculate a model comparison at the agent level. So here I put the code to sort of aggregate it by agent, and then to put it in a format that we can visualize. And here we see on the x-axis the number of the agent. The first 20 are the simple agent. The second 20 are the weighted agents. On the x-axis, the ALPD difference, which is centered at 0, meaning that everything that's below 0, there's better evidence for the simple agent model. For values above 0, there's better evidence for weighted agent models. What do you think is happening there? Yes?
If I read correctly, it seems like there are more that's under 0 in the first 20.
Yeah.
So the simple agent seems to be better most mixes, and then it's the opposite. The agent is better.
Yes, exactly. So we can see that there's about a 0.7 accuracy for both groups. So the agents, the models are able to be mostly right in identifying which one is best, but it's not perfect, right? There's about 30% error, which is non-trivial. But still, right, if we do this kind of operation in our empirical data and we see that there is a widespread, that's a cue that we should be more careful in what's the underlying generating mechanism. Well, in 2 minutes, I'm really not going to cover that, so I'm just going to mention that, right? In traditional Bayesian approaches, we're always shown that, oh, it's your previous experience that shapes the way you take into account the current evidence. And it's really easy to just adapt the models and tasks to do that. So we assume that the error stays the same. But what we can do is also some other stuff. So for instance, we could have that first you sample n times, and only at the end we make a choice. And this would be how the code works. Or we could do something even more interesting. That is, there is a task called jumping to conclusion, which is often used in schizophrenia study, where you have an urn in front, you sample once, and then you can decide whether to spend some of your prize money to sample again, or whether you want to guess now. And so we can actually very easily tweak this model to both predict when the participant is going to keep on sampling and which guess it's going to make when they're going to make a guess. And so you can see that the sampling choice happens. You cannot see, but I can tell you that the sampling choice happens at every trial, but that only when the sampling choice becomes a certain value, then we have the color choice that is given and needs to be assessed. And only in those trials that log posterior probability for that Bernoulli gets put in, right? Which is kind of neat. And the model doesn't have any issues. We could have that the weights themselves are learned. For instance, using reinforcement learning. This is, yeah, blah, blah, blah. We can have socially reinforced learning. That is, we can model not only whether I should sample again or make a guess, but I could model a more complex scenario where I can sample myself. I can look at your choice. or I can guess, right? And all of these are simply adding 1 or 2 lines to the code. So it's actually quite, yes, quite simple. Not validating it, but writing the stand code. So the idea is that now we have a whole new set of models that we can play with. We can make them play with the old models, making even more complex ones. So we can also further innovate. For instance, the hierarchical Gaussian filter comes out of these models by saying, not only we learn the weights, but we learn how much we should learn at every step, right? And we can learn how much we should learn, how much we should learn at every step. What we're going to do next, and we're going to have 2 guest lectures, is we are going to move beyond just looking at the choice, as we've done so far, but actually integrate the timing of the choice to the choice loop. Next week, we have a lecture on drift diffusion models. We'll discuss them, and the week after, we'll have a lecture on psychometric functions. And after that, that means after Easter, we will do the final module that is on categorization-based models, which again will try to take some principles from cognitive theory and say, how would they play out in these very specific tasks that you will have to play and figure out. Good. Thanks. And I'll see you tomorrow. In terms of the assignment, sorry, just so that it's very clear, this week and next week is still dedicated to the assignment for the practical exercise. The week after, you have practical exercises that are on the psychometric model just to get a breather and something slightly different. And then we will have the final block will be the final assignment.